for organizing this wonderful conference and giving me a chance to speak here. And thanks to everyone in the audience for staying back till the last talk of the conference. And thanks to the organizers again for letting me have the final word on this conference. So today I'll talk about an unusual new phase of matter. This work was inspired by some experiments in the cuprates, but this phase is also interesting in its own right independent of those experiments. And the phase is called directional scalar spin chiral order. The work was done at Stanford, and it was supported by the Packard Foundation. So I'm thankful to many people for discussions and help on this work, but especially to Steve Kibbelson and Srinivas Rakho. So let me start with the inspiration for this work, the experiments that motivated this work. These experiments were done on the cuprates in the very famous pseudogap phase. So many of you are familiar with this phase diagram. We won't be interested in all the various phases and the details of this diagram, but just to put things in context, some experiments were done in the mysterious pseudogap phase of the cuprates, and the experiment in particular was the polar Kerr effect. So what is done in this experiment is the following. You take your system, shine linearly polarized light on it, the light reflects off the surface and comes back, and you measure the light that comes back. If the phase satisfies certain properties, then the light that comes back has a plane of polarization that is rotated compared to the plane that was incident, to the light that was incident. And usually, a non-zero Kerr signal is a sign of ferromagnetism, or something that has the same symmetries as ferromagnetism. So it could be a ferromagnetic moment or superconducting vortices, but usually it is interpreted as a sign of ferromagnetism. However, the experiments in the cuprates showed properties which were very different from ferromagnetism. For example, they found that the effect could not be trained by magnetic field. So what is shown here is the Kerr angle as a function of temperature, and what I'd like you to focus on is this bump here. The different colors correspond to different externally applied fields, but as you can see, the bump always has the same sign. So these fields vary from +4 to -4 Tesla, but the bump always has the same sign. So they found that the sign of the signal could not be trained by a magnetic field, which suggests this is not some ordinary form of ferromagnetism. They also found that on flipping the sample, so they did the experiment on one surface, then flipped the sample over and did the same experiment on the opposite surface. If this was some ordinary form of ferromagnetism, you would expect the sign of the signal to be opposite in the two experiments. But what they found is that the sign was the same. The two colors correspond to the two different surfaces. They also noticed some other unusual features in these experiments. So what is shown here is, so what they did was they heated the system to temperatures well above the onset temperature of the Kerr effect and cooled it back down under various fields. So if this was some usual spontaneous symmetry breaking, then on cooling you would expect the sign to be picked up randomly. But again, they found that the sign was always the same. So these things are very unusual. This is certainly not ferromagnetism. In fact, another set of experiments, NMR, which is usually very good at detecting any form of magnetism, ferromagnetism, antiferromagnetism, some complicated, any kind of magnetic order is, it's very difficult for NMR to miss it. But NMR did not see any form of magnetism. So not only do these experiments suggest that this is not just ferromagnetism, but there isn't any form of magnetism present in these systems. So, yeah. Yeah, that's an excellent question. So what is happening here is, this is where the superconductor is formed, and the curves to the left of this temperature, Tc, this signal is because of the superconducting vortices. And they show a dependence on the magnetic field. So they can be trained by an external field. But above that temperature, you cannot train it with a field. So how do we reconcile these experiments? The key realization is that although usually the Kerr effect is interpreted as ferromagnetism, strictly speaking, it only needs time reversal symmetry breaking, not necessarily ferromagnetism. So therefore, this motivates the question, can we write down a phase of matter which breaks time reversal but has no magnetic moments? So this was the inspiration for this work, but these experiments and the question that I just stated motivates a more basic and more general goal. So let me define that on this slide. In most phases of matter that we know that break time reversal, in fact, all phases that I know that break time reversal, you can always find a set of, okay, some animation is not showing up well, but what I've written here is that you can always find some set of total angular momentum operators so that the sum of their expectation values in the ground state, that is what this is supposed to be. So that is the sum over all these operators and the expectation value in the ground state. You can find a set of total angular momentum operators so that this quantity is extensive. It's proportional to the volume. And common examples are ferromagnets, where Ji is the total angular momentum or spin operator on each side, antiferromagnets where the Ji changes sign between different sides and there are various chiral phases. So it's clear from these pictures that you can always find a set of total angular momentum operators so that this quantity, the total expectation value, is extensive. And therefore, and moreover, if you melt these moments, time reversal symmetry is immediately restored. And therefore, for very good reason, time reversal symmetry breaking is considered synonymous with magnetism. Because in all phases that we know so far, they appear and disappear together. However, this is not strictly true, because magnetism breaks some spatial symmetries in addition to time reversal. So therefore, we can ask the question, can we write down a phase of matter which breaks time reversal but has no density of moments? The moments could be spin moments, orbital currents, or some combination of those. But we want a phase of matter that breaks time reversal but has no density of moments. And in this question, I'll present one such phase, which I'll call the directional scalar spin chiral order. So without further ado, let me write down the phase. The simplest version of the phase is easiest to write in one dimension. So consider a spin chain made up of classical spins where the spins are ordered as shown. So the first spin points up, the second one points to the right, the third points into the plane, and so on. This pattern repeats. It's easy to see that a triple product of this form, where you take spins on 3 consecutive sides, so this has a non-zero expectation value in this orderic pattern. Now this phase clearly breaks time reversal, but this also has magnetism. And that is not what we want. However, there's a very powerful theorem in quantum mechanics and classical mechanics in a way, that if you start with a Hamiltonian that is spin rotation symmetric and is local, then promoting these spins to quantum objects immediately will restore the spin rotation symmetry, because that is a continuous symmetry. So the theorem that many of you know is, which I have not written here, but I should have, is called Morman-Wagner's theorem, which says that continuous symmetries cannot be broken in one dimension, but discrete symmetries can. So the key idea is, you imagine such a phase forming, you imagine this as a precursor to the phase you want, but then recall Morman-Wagner's theorem, which will melt the continuous symmetry breaking part of this phase. But this triple product also breaks a discrete symmetry, which is time reversal, and that can potentially remain unbroken. That can potentially remain broken. So now we have a phase which breaks time reversal because of this triple product, but it does not break any, it does not have any magnetism, because spin rotation symmetry is restored. So this is the one-dimensional version of this phase. Well, some animation is again not showing here. So what this is saying is this changes sign under time reversal, but it is invariant under spin rotation. Yeah.
Take a picture like this, where there's a certain handedness, and then I rotate every axis by a certain amount, I get another picture, and I keep doing this and take a superposition of all of them. Is that?
No, so that won't be the right wave function, because that will still have the correlations of the broken symmetry phase. Okay. So the wave.
So even though the net moment there, okay. So you don't also want the correlations of the.
Yes, yes. So it won't just be superposition. It's something a bit more complicated. And I'll say a few words about that in a couple of slides. So that was the one-dimensional version of the phase. In 2D so in 2D, Mermin-Wagner theorem allows you to break continuous symmetries at 0 temperature, but it is known that thermal fluctuations can restore continuous symmetry. So in 2D, this is not a strictly quantum phase, but it's a finite temperature phase. And finally, in 3D, we can use the same idea, but in 3D, it's known that thermal fluctuations allow continuous symmetries to be broken at any temperature. But we want continuous symmetries to remain unbroken, and the key ingredient we need in three dimensions is random field disorder. So this is another theorem that is known, and I won't prove or argue for that here. We'll just accept that if you have a system with continuous symmetries, and somehow there are some random fields in the system, then the random fields will restore the continuous symmetries. So the disorder average state will not have any broken continuous symmetry. So the basic idea is we want a discrete symmetry to remain broken, and we want to restore the continuous symmetry. And these are various ways of doing that in different dimensions. So it's important to contrast this with some other, so scalar spin chirality is not an entirely new concept. It has been discussed in the literature in many contexts before, but it is important to contrast the phase that we are talking about here, the DSSCO, or the direction scalar spin chiral order, with other examples of scalar spin chirality. So in all the examples that I've come across, the three spins that have chiral correlations are on the three vertices of a triangle. So these objects, the scalar spin chiral objects, usually appear in lattices which have some triangular motifs, like Kagome or triangular, or in 3D pyrochlore lattices. And in all these examples, the three spins that have chiral correlations are on the vertices of a triangle. Now, it's easy to check that purely based on symmetry, chiral correlations between these spins allow a magnetic moment perpendicular to the face of the triangle. And that breaks a discrete symmetry. So although the spin chirality itself is spin rotation symmetric, there is a different discrete symmetry that is broken here. And that discrete symmetry also, breaking that discrete symmetry leads to some magnetic moments. It leads to a flux that comes out of this triangle. In contrast, in the DSSCO, the three spins are in a straight line. There is no triangle through which a flux can come out or come in. And therefore, there's an important difference between these two phases, which is in the DSSCO, not only is there no magnetic moment, but purely because of symmetry reasons, if there were some other itinerant particles, they are also not allowed to have any orbital currents, any circulating currents, which is very different from these examples, where itinerant particles can develop, can have orbital currents and develop a moment. So we've been talking about what the phase looks like, but it's important to ask whether we can realize this phase in any simple, realistic model. So what I'll write now is, yeah. So these three spins are spins on three consecutive lattice sites. Right, so yeah, that's a very good point. So this picture does break translation symmetry, but the eventual phase is not this picture, but you start with this and then restore spin rotation symmetry. And that does not break translation. So you allow these magnetic moments to melt, but retain the discrete symmetry breaking part of this order. That won't break translation symmetry. Yeah, so I think neutrons will be able to see this at very short distances and short times. So I'm not completely sure about how that will work, but I think neutrons will be able to pick up this tripling of the unit cell. Yes. Right, so far what we've seen is, so we defined the problem statement, which was inspired by some experiments in the cuprates, and defined a phase which is, which realizes the goal that we wanted, which is a phase that breaks time reversal without having any magnetism. But it's important to ask whether we can get this phase from a simple Hamiltonian. Otherwise, it's not that interesting. So what I'm going to write down is a couple of Hamiltonians which are simple. These are guesses for the Hamiltonians, and the guesses have been made in such a way that they probably lead to that phase, but I have not checked that. And if there are any students in the audience who like doing numerics, like DMRG or any numerical calculations, this would be a good problem to get your hands dirty. So this is the Hamiltonian. It contains Hamiltonian in 1D, and let's assume the spin is greater than half for now. So the Hamiltonian has three terms. The first two are biquadratic interactions, and we assume all these coupling constants are positive. The first term is a positive biquadratic repulsion, biquadratic repulsion. This ensures that any two, if these were classical spins, this would encourage any two neighboring spins to be mutually perpendicular. The second term is a biquadratic repulsion between next nearest neighbor spins. So this encourages the next nearest neighbor spins to be mutually perpendicular. And the third term is a third neighbor ferromagnetic interaction. So the first two ensure or encourage any three consecutive spins to be mutually perpendicular, and the third term repeats the pattern along the chain. So, okay, as I said, I've not checked this works, but I would be very surprised if this never works. So this is for spin greater than half. For spin half, this Hamiltonian won't work because you can check that a biquadratic term reduces to a quadratic term if spin is half. So for spin off, we have to do something more. And here is another guess which probably works. There is one term which is nearest neighbor Heisenberg term. It's not very important what the exact form of this term is, but the second term blatantly promotes this scalar chiral order. So again, for a large enough value of G, this probably gives the chiral spin order phase. It turns out that you can write this in a bosonized form, but that I don't think it's very important for now, so I'll skip over that. So we've defined the phase and guessed some Hamiltonians. And this work was inspired by experiments in the cuprates, so let us come back to that and let's see how far this phase helps us reconcile or try to reconcile those experiments and some others. So the first experiments I mentioned were Kerr effect experiments. We saw that the experiment saw that the Kerr signal was untrainable magnetic field. It had the same sign on opposite surfaces. It showed a memory effect above the Kerr transition temperature. And what was also observed was that the magnitude of the signal was very small compared to some usual ferromagnets like strontium ruthenate. The second important experiment was that NMR did not see any magnetism below the Kerr transition temperature, the Kerr onset temperature. There are some other experiments which have also been performed in this phase. In fact, many experiments have been performed, and it is impossible to cover all of those. So I'll cover some fairly large subset of those. And we'll see that the DSSCO phase helps in reconciling, well, goes a long way in reconciling many of those experiments. So one other important observation was that X-rays saw charge ordering tendencies at the Kerr onset temperature. Now this is surprising because the Kerr effect is it requires time reversal symmetry breaking, but charge order does not break time reversal. So there is no reason why a charge order and the Kerr effect should onset at the same temperature. The Some nurse effect experiments found nematicity above the Kerr onset temperature. So many of these cuprates have a four-fold rotation symmetry, but it was found that even in the four-fold symmetric systems, there were some hints of nematicity of this four-fold symmetry breaking above the Kerr onset temperature. And in thin films transmission experiments, some optical transmission experiments saw that vertical reflection symmetries were broken below the Kerr temperature. So these are many experiments that one would like to reconcile. And we'll go step by step and see how far we can get with each of these experiments with the DSSCO. Yes? Mhm. So, uh-huh. So they are fairly close. You can go back to the very first slide. The Kerr onset temperature is quite sharp. So this temperature is very sharp. And the charge ordering tendencies onset at some temperature which is quite close to this, and that transition is also quite sharp. So yes, maybe within a few degrees, but so I've not shown the X-ray data, but that is within a few degrees of this temperature. So yeah, maybe they are different, but so this is in the underdoped regime around here. Okay, so here is a plausible phase diagram. This is, so everything that I'll argue here is phenomenological. Uh, there are things in the microscopics that still need to be worked out, but we can still get a long way just using phenomenology. So here's a plausible phase diagram. The proposal is that the DSSCO phase forms at some temperature T sub D, and the charge order onset forms at some temperature that is on this diagram is labeled T sub K. And let's see what we can do with this. Firstly, because the Kerr effect has some contribution from the DSSCO phase which does not couple to a magnetic field because it has no magnetic moments. So clearly this effect cannot be trained by a magnetic field. Secondly, if we assume that the charge order is symmetric under flipping the sample, okay, again, some animation is not showing very well, but what this is saying is the combination of the combination of the DSSCO and the charge order preserve a don't change sign under flipping the sample. And therefore, let me backtrack one step. So before going through this list, let's focus on this phase diagram again. The proposal is the DSSCO forms at some temperature T sub T, and at a low temperature, the charge order forms. Now in this yellow region, it turns out all the time reversal is broken. There are some vertical mirror symmetries, and that kill the Kerr effect. So time reversal is broken, but we still have not broken enough symmetries to give a Kerr effect. But this charge order breaks those mirror symmetries, and below T sub K, the combination of the charge order and the DSSCO give a Kerr effect. So that is the basic idea. And now we can go step by step through this list. So the effect comes from this combination of charge order and the DSSCO, neither of which couple to a magnetic field. So therefore, the effect cannot be trained by a field. It has the same sign on both surfaces, assuming the charge order does not change sign under flipping the sample, and that is not unrealistic. There are some models that I can write down and show you later if you are interested. Fairly realistic models. So this also explains why charge order onsets at the same temperature as the Kerr signal, because it's the combination of these two phases that gives you a Kerr signal. Now the DSSCO clearly breaks four-fold rotation symmetry because the chiral ordering exists only in a particular direction. And therefore, that way we can argue why some nematicity is seen above the Kerr temperature, that is in this region. The memory effect can be explained as follows. So you heat above the Kerr temperature, but let's say you're still below T sub D, then the time reversal symmetry breaking part of this order is the same. And usually the way the crystals are built, or once a crystal is built, it contains some dislocations which fix which way mirror symmetries are going to be broken. So even if you go to a temperature that is well above the Kerr onset temperature, these dislocations are not going to change much. And therefore, the way the mirror symmetries will be broken, once you come back down below T curve, will also be the same. So in short, the mirror symmetries and the time reversal symmetry breaking part will have the same sign once you go above T sub curve, but stay below T sub D and come back down. The small magnitude can be understood because the Kerr signal depends on the existence of two order parameters. So this part, well, again, the animation is not showing very well. So what I've drawn here is I've put check marks on all the other lists, but for NMR, I put a check mark and then put an approximation sign in front of it. Because it turns out, once you break some mirror symmetries, you are allowed magnetic moments, but these magnetic moments are going to be very small again because they require the existence of two order parameters. And the NMR experiments so far, well, so it's possible that they are too small to be detected by NMR, especially because these experiments are not looking for very small moments, but they're looking for relatively larger moments. And finally, so the charge order breaks some vertical reflection symmetries, and that is what is seen in the transmission experiments. So a large number of a fairly wide set of experiments can be reconciled using this DSSCO idea. And that is one of the main punchlines of this talk. So how do we check if this is true? There's a very simple experiment that I'll state here. We won't go through all the arguments. The proposal is you sit above the Kerr onset temperature, sit above T sub Kerr, drive a current through the system. The statement is, if the chiral ordering is along X, then driving a current along Y should produce a Kerr effect that is trainable by this current. So if you reverse the current, the effect should change sign. But driving a current along X should not give a Kerr signal. So this is a very sharp test for whether the right symmetries are, whether this idea of two-phase transitions is correct. And this is a table that where I've worked out what symmetries are present with the DSSCO only and with currents in each direction. So here's a summary of the talk. There are two main results. One is it's answering a theoretical goal that is independent of the cuprates, which is we've written down a phase of matter that breaks time reversal but doesn't have a density of moments. This is almost surely not the only phase that does that. I'm sure there are more, but this is one simple example where that happens. And it turns out using a phenomenological picture that contains the DSSCO goes a long way in putting together many experiments on the cuprates which have been difficult to understand so far. There are a few things to be ironed out, a few loopholes, if I may, to sort out. So one is there are some microscopic issues. What exactly are these spins? Are these spins on the copper or oxygen or some combination of those? Effects of spin-orbit coupling, whether the Hamiltonians I wrote down are achievable. So there are various microscopic issues that need to be sorted out. And even the Hamiltonians that I wrote down, I thought they work, but it would be good to check that. If you think this phase is interesting, it would be good to search for those in other materials as well, because we know the symmetry group of this phase, and you can ask your experimentalist friends who know how to make materials to look up a table or use their intuition to find other materials which might realize this phase. And finally, this was inspired by the cuprates, and it would be good to see if this actually exists, and if you have good, if if your experimentalist friends and you think this might work, I'd encourage you to persuade them to do this experiment. Right. Thanks for your attention.
Questions?
Okay, so one question regarding this Mermin-Wagner possibility that this discrete thing may be broken, but the continuous thing is preserved, right? So I know some classical spin systems and there's something similar might have happened, so let me ask you that. There's maybe a relation. So these are continuous degrees of freedom, some spin systems, and they interact through some short-range interactions, and they're 2D systems, okay? So by Mermin-Wagner theorem, I cannot expect any continuous symmetry breaking at finite temperatures. But some of these things may show a nematicity, which is uniaxial, right? So that's like a discrete object.
Yes.
But in all these things, I don't know of a single case where there's a finite temperature transition for the uniaxial nematic. So, okay, so the way I was thinking about it is, okay, you have continuous spins, so you choose some discrete direction, but even that discrete direction lives on a sphere, so first you have to pin that, and then there is some Z2 there or something. So if that happens, then again, it's not clear how you can escape Mermin-Wagner.
So in that example,
Right.
if I understand this right, the continuous symmetry has to be broken for you to be able to define a discrete direction. So, okay, so that is the opposite order of symmetry breaking that we want here. Okay, so I'm not sure what would be a right or a good answer to this, but I think the discrete part is simply the correlations between three spins, which can have two signs, two possible signs. So I don't know if that answers the question, but I'm not sure what is the way to answer this question. Yeah, maybe we can continue this later.
From neutron, we sort of know in curates that the nearest neighbor exchange is about whatever 100 Kelvin or something. It's such a big nearest neighbor exchange will probably screw up all of these things, the test Hamiltonians that you were talking about. Or is it possible to get test Hamiltonians in presence of large nearest neighbor exchange, which we know exists in curates, where we will get this sort of thing?
Okay, so before answering that question, I should mention that neutrons will screw up something even more, which is neutrons actually see magnetism. So in some way, some sense, neutrons and the Kerr results are consistent with each other. But NMR is in direct conflict with that. So firstly, one has to make a choice between neutrons and NMR. And so I chose NMR. So now to answer your question, so your question was, if there's a large nearest neighbor exchange, I think it is possible because, so at least intuitively, I don't see why nearest neighbor repulsion is going to ruin anything. Yeah, nearest neighbor antiferromagnetic, so by repulsion I meant antiferromagnetic exchange. So I don't see why that is going to spoil anything here, as long as, yeah, it will promote nail order. So firstly, we need biquadratic interactions. If you don't have that, then you're dead already. So if the nearest neighbor exchange is larger than the biquadratic interaction, then you have to throw this out of the window. Yeah.
Some picture of circulating current.
Yes.
So that would not give effect or no?
Yes. So there are several versions of that picture, and one of those gives the Kerr effect with the right symmetries. but that also predicts NMR, or a very large NMR night shift. And that has not been seen. But that is consistent with the neutron experiments.
Can you just go back to the Hamiltonians that you wrote down? Right. So I'm just trying to understand something. So is it true that in the first one, if I look at spin-spin correlation functions, I'll actually see a modulation at 2 pi by 3, but I won't in the second one? Because you do have the sx dot sx plus 3. Like my picture is that somehow with the spin half you take a triad. The triad has the right chirality, 3 of them. Then you take the next 3. They have the right chirality, but the first spin of the first triad is not correlated with the first spin of the second triad. Is that the way I should look at this state?
Wait, so you take a triad and then, so triad on 1, 2, and 3, and the next triad on...
the right chirality.
Okay.
Then I take another triad, which again has a right chirality, but I look at the first spin of the first triad, the first spin of the second triad, which are third neighbors now, but there's no correlation between them.
No, there is, that is...
No, that is for this one, but for spin half is that... No, that's what I'm asking. So in the first one, there would be a 2 pi by 3 modulation, presumably, coming from that term, whereas it seems to me that in the second one, there wouldn't be. Unless my picture for what the state for the second one is wrong.
Yeah, I think you're right. So for the second one, I should probably add...
Well, I mean, it's just a question of whether you get a 2 pi by 3 modulation or not. And I would think that in the first one, you would definitely have 2 pi by 3 modulation coming from the last term. Second one, it seems to me that you probably wouldn't.
Yeah, so if you don't, then you don't get the correlations between...
Right, the first spin of each triad.
Right, right. Okay, so I should probably add a ferromagnetic term here to make it consistent.
No, but I'm saying I'm talking about correlations. I'm not saying that there's any translation symmetry breaking. Yeah, but I'm asking if that is going to be the ground state of the Hamiltonian that he wrote down here. Because, again, my picture for that ground state...
Yeah, so I think...
Right. Right, so it would... Right, it would... Okay, so it would give... So there's an interaction between the third spin of every triad.
No, so that is, no, so I think what he's saying is right. So with the second Hamiltonian, 1, 2, and 3 might have, say, have the positive chirality. If 2, 3, and 4 have the opposite chirality, which also still minimizes this term, so then the 1, 2, 3, and 4, 5, 6 will have opposite chiralities. So yes, it should reduce to that, but they should appear with the right coefficient so that this kind of order is favored. I mean, yes, you would see that in the Magnon spectrum. So we don't know if this Hamiltonian actually exists in the cuprates or any system that we know. Yeah, so this Hamiltonian probably doesn't work for the cuprates. So this is a potential Hamiltonian that might give this phase in maybe some other system. Yeah.
Meant about the first Hamiltonian. So presumably because of this biquadratic terms, you would also get some quadrupolar phases, the spin nematic type of phases.
So does that also happen with positive biquadratic?
Yeah, it's just antiferro type of ordering. But
I see.
So that's also a concern. Yeah, but not in 1D again, power law, right?
This is 1D.
Power law. But the question about the order that you are speaking, in context of cuprates, it's Z2 cross Z2 order parameter, one Z2 being the Ising nematic type of thing, the other Z2 being time reversal.
Yeah.
So is there any way to restore time reversal without restoring this nematic order, lattice nematic order in your picture?
Yeah, so charge order does that. So unidirectional charge order does exactly that. It restores time reversal, but doesn't break that. Breaks the pneumaticity. I mean, it has pneumaticity.
That would be like the picture that you drew, but the other way around, the charge order setting up first, followed by this order.
Yeah,